So we're going to look at titrations, and all titrations is where we take one reagent and we gradually add it to another until we can kind of see that the reaction is finished. And that's really what this statement up here means. So how a titration is set up is we have a burette, which is this guy right here. This is just a funnel, and I didn't label that, but I should. And we just use the funnel to pour in the titrant that we're going to be using. And so the substance that goes in the burette is what we call the titrant. In this example that I'm going to show you, it'll be sodium hydroxide. Now, sodium hydroxide will have a concentration of 0.25 moles per liter. And the volume of sodium hydroxide that we're going to use to neutralize the substance that's down here in the Erlenmeyer flask is unknown at this point. That's the point of doing the titration, is to figure out how much of this stuff we're going to need to add in order to complete this reaction. Down here in this Erlenmeyer flask, we have what our substance, which is called the sample. And in this case, our sample is hydrochloric acid. And it's going to have a volume of 10 milliliters for each trial that we do. And normally we would do at least 3 trials, but sometimes maybe a few more just to ensure some accuracy. But when we do a titration, you'll hear these statements where we've got the titration of something with something. So the substance that is mentioned first in that statement is what we call the sample. And so the titration of our sample with our titrant is how those phrases get laid out. And so in this instance, because our sample is hydrochloric acid, we're going to say the titration of hydrochloric acid with our titrant, which is sodium hydroxide. And so that's how that statement is placed out, like that. Now, our diagram, or our table right here, is where we're going to collect our results. And a couple of rules that we have to follow as we're doing these. First of all, number 1, we have to collect a minimum of 3 trials that are all within 0.2 milliliters of each other. Now, you have to be careful. It's not 2 milliliters, it's 0.2, so a tenth of a milliliter, which is a pretty high level of accuracy that is expected when we're doing a titration, but is definitely possible. Some things that we just need to be careful of is human error and just making sure our measurements are quite precise, and then it should be fine. And then once we get those 3 trials that are within 0.2 milliliters, then what we need to do is we need to average those 3 trials to get an average volume. And then we use that number in our calculation. So in this example right here, you can see the numbers that were collected. You can see trial 1, the initial burette reading was 0, the final burette reading was 9.6. So the amount used was 9.6. We just go final minus initial. And then trial 2, you can see the amount used was 10. And then trial 3 was 9.7 and trial 4 was 9.5 milliliters. And so you can see that trial 1, 3, and 4 are the 3 trials that are within 0.2 milliliters of each other. And trial number 2 just was a little bit more. It wasn't within that 0.2 range, and so we considered that trial burned. It's not a trial that we use in our average calculation. We're only going to average, and that's really important, we're only going to average the trials that are within 0.2 milliliters. If you had all 4 trials that were within 0.2, great. If you only had 3 of the 4, then you only average the 3 that are within 0.2 milliliters. And finally, when we do the titration, in order for us to know that we've reached this identifiable endpoint, and it's an acid-base reaction, what we do is we add 1 drop of phenolphthalein into this beaker here so that we can see when the reaction is finished. So this phenolphthalein will change colors for us. Specifically, that we're looking for a persistent pink is what we call it, to find out when the sodium, or when the hydrochloric acid has been completely neutralized by the sodium hydroxide. The point of doing a titration is to get this volume right here. We know the volume of the hydrochloric acid, and the stoichiometry that we're going to do at the end is going to help us calculate what the unknown concentration of the hydrochloric acid is. But in order to do the stoichiometry, I need to know how much volume is required to neutralize 10 mils of hydrochloric acid. And so in order for us to figure out what this number is, we have to do this titration and figure out what that volume is so that the numbers can be used in stoichiometry. And that is what this number is right here. We did the titration. We're going to plug that number, which is our average of our 3 trials that were really accurate, and we put this number in right here. This is the volume via the titration that we have determined is the amount that's needed to neutralize 10 mils of hydrochloric acid. And so now using this information, we can do some stoichiometry to figure out what is the unknown concentration of the hydrochloric acid in this sample. And so in the next couple of clips, I'm going to demo for you what this titration really looks like using the actual equipment, and then we'll look at some titration curves as well. Okay, so just a short demo for you guys on a titration, what it looks like exactly with the apparatus. So what we've got here is our burette. You can see it's this long skinny tube that I stick solution into. You can see I've already put the titrant in here, sodium hydroxide. I did so with a funnel, and then I've got it clamped to this stand right here using this clamp. The clamp isn't done too tightly just because you don't want to crack or wreck the burette. They're quite expensive, so you want to make sure you're being gentle, but making sure that it's on there snug and not going to slip or fall as you're doing your experiment. Then down here below, I've got you can see my 10 mils of hydrochloric acid, and again, I pipetted that out previously and just put it into the beaker. And then what you're going to want to do is you're going to want to take some phenolphthalein or whatever indicator you choose to use and put 1 drop of that in here, and I've done that already as well, so we're ready to go. Now before we get started, what you want to make sure that you do is make sure that the tip of the burette is full, okay? And normally you would empty that out into a small beaker underneath, because when you start to add volume to this, if the tip of the burette needs to be full. If the tip of the burette is empty and you turn this open a little bit, the volume here in your measurement is going to go down, but you haven't actually added anything to the solution. So you just open this really ever so slowly, and the air bubbles start to come out. And if you go ahead and do your first trial like this, then you will have measured air being added to your reaction, and that's not what you want to do. So grab an empty beaker, empty this out into here. I'm just going to add it into this because I'm not needing to be precise with my demo, but you want to make sure that you are adding or you're getting the tip full of the solution so that there's no air left in the tip. If you open it too quickly, then the tip won't fill up entirely, and you always have a little bit of an air pocket inside of there, and that will affect your results as well. So now once you're at this point, you want to make your initial burette reading on your burette, making sure that you're making your measurement at the bottom of the bubble that sits inside of the burette, not the top, because the bottom part is the most accurate. And then you're going to make your measurement right here in your initial burette reading for trial number 1. And you want to keep track of those things so that you can calculate how much was used when you finish the trial. So now what you're going to be doing is you're going to be looking for that persistent pink. You can kind of add a bunch here at the start, just because the first little bit is going to react quite quickly. But once that pink takes a little bit longer to disappear, then you know you need to kind of slow down the addition of your titrant to your sample. So we're still at this point where that pink is disappearing quite quickly still, so you can add a little bit more in and stir it and mix so that pink disappears. And now that pink is taking a little bit longer, so I want to go just a few shorter bursts of the titrant just to make sure that I don't overdo it, because once you burn the solution, like you can see I did right there, then there's no going back. And so you got to add it gently and slowly, 1 drop at a time, so that you don't burn the solution. I'll be right back with one that doesn't look burned, but that's what a burned solution is going to look like. I'll do one more example of myself kind of doing it a lot more slowly to show you what the persistent pink looks like. All right, so this solution right here is really close. I've added some. And so now I want to go really slow because the pink takes a little while to disappear. So if I can turn it 180 degrees like that and then mix it around, That's a gradual way of doing it. Or you can open up this just a little bit and you can just kind of let it drip in as you mix. Now, that was like 2 or 3 drops, and it was taking some time for it to go away. So now that's clear again, but I'm probably 1 more drop away before this is at its end point, and that persistent pink that I'm looking for. So the persistent pink is really if I'm mixing, and for about 10 seconds, that pink hangs around, and then eventually the solution goes clear again, then that's my end point. I want to stop there and I want to make my final Barrett reading and record it in my chart over here for trial 1. And so you go really carefully, just opening it ever so slowly till 1 drop drops in. You can pull it away to make sure not another drop drops in, and you can stir it. And you can see right there, that kind of stays a bit of a tingy pink color for quite a few seconds before it goes clear again. And so then I would stop there and I would add in my, I would write in my final Barrett reading right there, and then do my calculation and calculate how much was used. One last thing you want to make sure you're watching out for is that when you do a titration, make sure that your titration, your titrant here, doesn't get below the last measurement on the Barrett. Because if you get it down here and then it's like, okay, I've reached my end point and I go to make my measurement and it's like, oh, darn it. What number am I at? There's no numbers here. So you got to make sure that when you're doing your trials that you always have enough titrant to complete the trial. And so if we take a look at what the burn solution would look like, even just 1 or 2 more drops here, you can see that this is going to end up that dark pink, and that's not what we're looking for. So hope this is helpful, and it gives you a sort of a visual on what titrations looks like and how to do them. So when we do titrations, what we also have to deal with are titration curves. And this is an example of a titration curve right here. The titration curves are set up like this. We have pH on the y-axis and the volume of the titrant added on the x-axis, usually measured in milliliters. And you can see that this is the titration curve of the example that we've been going through in this video, where we have the sample and HCl being titrated with the titrant, which is NaOH, sodium hydroxide. Now, titration curves look like this, where they have these 2 flat regions and then this area where there's a sharp rise in pH. Because right here, if we start the reaction with just HCl in the beaker, in the Erlenmeyer flask, and we add just say 1 or 2 drops of NaOH to that NaOH is going to react really quick, and it's going to be gone. And there's going to be a ton of excess HCl still left in the beaker. Because there's acid left in the beaker, the pH is going to be quite low. Because it's HCl, it's a strong acid, it's going to be very low. But if we continue to slowly add NaOH to the solution, eventually there's not going to be any excess HCl left in the beaker, and that's what we're trying to get to. Trying to get to this point where we can neutralize the strong acid with the strong base. And when we do that, we've reached what is called the equivalence point. The equivalence point being the pH of 7, where we've neutralized the acid with the base, and there's no extra acid and no extra base in the beaker. It's just a very equal amount that has been added so that the pH is 7. If we were to add another drop or 2 of NaOH, then we would get to that burned portion that we talked about in the previous clip, where now the solution has been burned and we can't use it in our calculations, and so we'd have a pH somewhere around here. If we just continue to add NaOH, then we would just have a pH that's really high because we're adding NaOH to more NaOH, and so that's just why that's nice and flat there. Now we have 2 points really in a titration. We have the equivalence point, which is in this course going to be a pH of 7, the point of neutralization of the strong acid or the sample that's being reacted. And then we have the end point, which we talked about in the previous clip, which is the color change of the acid-base indicator that we're using. Now, this red box here is what indicates what would be a good range of a pH indicator to use for this particular reaction. You would want to pick an indicator that has a pH range that sits around the equivalence point, because there's no way that you're going to be able to know when you're physically doing the titration that you've reached the equivalence point if your end point, the color change that the acid-base indicator turns, is down here at say pH 2. if the color changes at pH 2, that's not going to be a good indicator to pick, because you're going to want to know when you've reached pH 7. So to pick an indicator that has a pH range around 7 is going to be a lot better and more helpful for you when you're doing your titration. So the point here in a titration really is to choose an endpoint that is going to be around the equivalence point. Now, because the endpoint is just an observation that we make, it's a color change, deals with qualities, this is qualitative analysis. The equivalence point, on the other hand, is a number that we can actually calculate. The calculations are not something we do for this course, but it is a number that can be calculated, and so because of that, this is a type of quantitative analysis that we do for these titrations. Now, for this titration curve down here, all this really is that what we can do with titrations is we could flip from our previous example the sample with the titrant. And so let's say if we had now hydrochloric acid in the burette and sodium hydroxide in the beaker down below, then I would have now a titration of NaOH with HCl, and so my titration curve would be flipped, as you can see here. And so I would start with a high pH and end off with a low pH. But again, the equivalence point would still be at 7. So the last thing you need to know about titration curves is really just that, is that we're titrating in this course strong acids with strong bases or strong bases with strong acids. And when we do that, the equivalence point will always be 7, because we're going to get a nice neutralization right at that neutral point of the pH scale. Okay, so an example to show you how the stoichiometry goes for this and how we take the data collected from the titration and apply it to solution stoichiometry. So here's our balanced reaction. Again, stoichiometry, rule number 1, write a balanced chemical equation. So hydrochloric acid reacting with NaOH, and there's my products over there. I've written my information down below that was given to me in the question. Now you'll notice that this number right here was not given to me in the question, but it was the number that I found from doing the titration. So here's the data again that was collected from the titration. Remember, I took the average of the 3 trials, 9.6 plus 9.7 plus 9.5 divided by 3 is 9.6. So that 9.6 is an average of those 3 trials within 0.2. That's really important that you remember to do that. And that average number is what goes in right here for your titrant. And so the volume of my titrant used to neutralize HCl was 9.6 milliliters. And then at this point, I can calculate what the question was asking for, my unknown concentration of hydrochloric acid. And so I just do the stoich by step number 2, calculating the moles of the given. 9.6 times by the moles per liter, or the concentration, will give me the moles of NaOH. And then you can see that NaOH here cancels. These moles cancel, and I'm left with hydrochloric acid, and you can see that those milliliters cancel as well with those milliliters. And so I just plug that into my calculator. I end up with 0.240 moles per liter, and that's my unknown concentration of hydrochloric acid.